Good morning, afternoon, everybody, wherever you are. And we're about to start our session, but we're giving people a chance to join. So give us a few minutes while the last people can join our session. Okay, it looks like whoever wanted to be here is here now. So welcome to this Intro to Supercomputing session or workshop. My name is Ramses van Zon. I am one of the analysts at SciNet, SciNet being the Supercomputing Center at the University of Toronto. This is a workshop that sort of takes the place of what used to be our summer school, or one of the sessions of it. We used to have a whole week-long summer school, and people would come and in person learn in several streams. And this is sort of the alternative to it, online, and in a way that I hope fits people's schedule a little bit better. So this week is dedicated to learning about supercomputing. So it's going to be a little bit more general, but there's a lot of things about supercomputers or large-scale computing that are quite a bit different from running things on your own laptop. So we're going to go into that, and we'll actually get a chance to try these things out on an actual supercomputer, even if you didn't have access to one. And so that's going to be the aim of this week, to get you familiar with these computing machines. So it's intended to be a fairly high-level primer, but we will do some exercises that you kind of have to know a little bit of Bash shell, so Linux shell for it. Otherwise, you can still follow along, but you might not be able to do every aspect of the assignment. We will talk about why people want to do supercomputing, also known as high-performance computing. How that changes things, why that isn't just getting a more powerful computer and running things on there. And as I said, supercomputers, they run on Linux, or at least some flavor of Linux. And so we will have to work on the Linux command line, at least a little bit. And that's how you would communicate with these machines in any case. So that's, if you're not too familiar with that, we have courses on Linux as well. And it's something that once you learn it, I find people tend to like it, prefer it. It's much more direct and intuitive, not intuitive, much more direct and versatile than working with GUIs. But it's also just a matter of fact, that's what we have. By the way, if you have any questions during the talk, I might not always have a chance to look at the chat, but we have other people from SciNet here, like Marcella, Bruno, and Alexei is here too. That can answer some questions as we go along. If they don't know, they can drop me and ask it. But feel free to ask questions, and every now and then I will check the chat and see what's going on. All right. So what do we need? What do you need to take this course, to take this workshop? So you'll need a computer with a browser and internet connection. Those of you that are here obviously have at least an internet connection. You'll need a Zoom client. Again, you guys have that. But you'll also need what's called an SSH client. So to connect to a cluster, to a supercomputer, you have to log in remotely, and we work with the SSH protocol primarily, and so do most other supercomputers. If you're working on a Linux machine or a Mac, not Macs, a Mac OS, you tend to already have SSH as a command in the terminal. So you open a terminal and you can type SSH and then something behind it that I will specify in a second. If you're on Windows, it tends to not to be their standard. There's a lot of options where you can get a Linux-like environment in Windows. One that is particularly quick to get set up and works even with like remote graphics is MobaXterm. So if you're on a Windows laptop or a Windows computer and you don't have SSH, download MobaXterm. There's a free version that works perfectly fine, and you'll be good to go. So the other thing you need to be able to do is to log into the website. We will take attendance, so we will know if you attended the 3 sessions that compose this workshop, and we'll do that by doing a little test on that website. So make sure you can connect and log in. Make sure you remember your password. It's the same that you use to get your stuff here. So today's attendance code. So if you go to the course, wait, I think I have it here. Yes. So we're at the first lecture. That's today. We'll give you an assignment at the end of the lecture to work on for the rest of the week. You can ask questions in the chat. There's also a forum on the course site, which is very useful outside of these lectures. And during the lectures, you can ask questions as well. On Wednesday, we'll have kind of what are a little bit like office hours. So hopefully you will have tried your hand at the assignment, or you might have some questions that are easier to ask in person. That session is really to show some examples to answer your questions. We will do it plenary, so anybody that has a question, everybody will see the answer. It tends to be a nice informal session, but I highly recommend to think of a question and come, or even if you don't, just see if you get some helpful hints. Then the assignment that we give, we've put a deadline on when you can submit it, and you submit it into, again, the course sites, and there's an assignment Dropbox where you can do that. The deadline is midnight Thursday, mainly because that gives me some time on Friday morning to look at them. They're not going to be like graded in detail. It tends to be too many people. We're already over 50 people here, so that I can't do that in the morning. But I can see what are sort of common pitfalls. And so I can address those on Friday. And the point of the assignment isn't to get it perfect. It's really to show that you've worked with the material and that you've tried something, even if it wasn't the perfect solution. At least you've learned something. And then on Friday, we'll actually address those common issues and present a solution to the assignment, and present some wrap-up materials, some other things, some other tips to run effectively on supercomputers. Let's see if there's any questions. Okay, so for today, the attendance test code is 1. People already asked. The midnight Thursday is actually 5 minutes to midnight. It's how the course website rounds it off, but I think it'll actually allow you to submit a little bit late if you're one of those people, and I used to be one of those that works until after midnight. That's okay. That's okay. But just imagine that if I wake up at, I won't tell you when, but say early morning, I should be able to see your assignments. Any questions about this, about the attendance test? Do people still have difficulties finding it? I don't see any questions, so we'll continue. Okay, so that's about the course. By the way, the course will have credits associated with it. So if you if you're present 2 of the 3 times in the workshop, because things happen, and you submitted an assignment, then you get credits, and those credits can be counted up. You don't get a badge for every workshop separately, but the way signed certificates work is that you add up these course hours or lecture hours, and once you have 36 of them in a particular topic, you can get a certificate. So you'd have to do quite a few of our courses. That is kind of on purpose, but this also counts towards scientific computing and high-performance computing certificates. Okay, so let's talk about supercomputing. It sounds very like from a comic strip, but supercomputing is also called high-performance computing, and all of these are, of course, relative terms. And the idea is that you need to leverage computations, large computations. And you have to use computers that are basically bigger than what you have in your own office. And so super really starts from when the computer no longer lives where you work. So this involves a number of things. It involves special hardware to make computers that are bigger, because if they could make a computer that is efficient enough or fast enough for your particular application, they would. So it's specialized hardware, specialized software as well, but also special algorithms. The way you have to use these machines is often running things in parallel. We will see that supercomputers are not computers that are 1,000 times faster than, say, your laptop, but they're 1,000 times bigger, by basically having more computers interconnected. So that means that you have to give all those computers something to do at the same time, or they're basically useless. And that in turn means that your algorithms, the way you compute things, have to be modified. So it involves basically the whole stack of computers. And that's kind of why it's different from just saying, okay, I know how to use a computer, and I even know some programming, and I know some scripting, and I run it. Now can I use a supercomputer? But all of these things start to matter when you hit the wall of your own machines. Okay. So why would you need that? What are some common cases on when you actually need a computer that is more powerful than your own? Either your problem takes too long, so you run it on your machine, and you try to figure out how much time it would take to run your computation to finish your PhD thesis, say, for instance, and you figure out that is, I don't know, 2 decades or a millennium or something. Basically, it takes too long, and so you either have to give up or you have to use a supercomputer. It could also be too big. Maybe you have a problem that needs a terabyte of memory, and you don't have that. That could be a reason to use a supercomputer. Or your data is just too big, so it doesn't fit on your hard drive. You have to store it somewhere else and also process it there, because that's kind of so there's too long, too big in terms of the system size, and too big in terms of the input size. Are reasons to have to use this. So some examples that are commonly run on supercomputers are computational fluid dynamics, molecular dynamics, smooth particle hydrodynamics, Monte-Carlo simulations, quantum chemistry, bioinformatics. And the last point is a bit of an odd one, because it's not really a field of study as much as a technique, but data science and machine learning touches upon all of these things. And they also need supercomputing in terms of, if you think of deep learning, the amount of computation you need to train a model is actually rather big, and so again, you need more than your own computer in many cases. Now, I'm a bit older than I think most of the attendees here, but I do remember the time of the free lunch, and by that I mean the era in which, when your computer was too slow to solve your problem, you waited a year or so, bought a new computer, and now it was 3 times faster, and your problem was solved. So that was actually a viable strategy. Like, your computer isn't fast enough, your program's not fast enough, you just wait. In those days, which ended somewhere around, which one's the clock speed? Around 2000, I say, 2005, clock speeds would increase. So the clock speed is basically the main frequency at which the computer can execute anything, like add something, multiply something, get something from memory. There's a finite tick at which these CPUs, these processors tick. They progress one step at a time, and those steps are very short. So the frequency at which these steps, these finite smallest steps occur, that's the clock frequency. And that used to increase quite dramatically until about 2005, when it was stuck to a few gigahertz. So that is billions of computations possibly per second. So you'd say that should be more than enough. But if it's not enough, there was no way to increase it. I mean, there is a way, but what happens as you try to make the frequency higher is that you have to have chips that consume so much energy that basically the chip melts under its own computations. And so you'd need enormous cooling systems to make that work. And although people have tried that, that is not economically viable. You cannot make machines that run more than that. And at some point, the only way to make it work is to make chips that have circuits of the order of atoms. And again, we won't be quite able to do that, although we're getting pretty close. So for all of these reasons, the frequency stopped increasing. And so we still want to, there was still progress in the power of computers in general, but it no longer came just by their main speed being faster. So the speed stays the same. Instead, rather than having faster hardware, you've got more hardware. And so every machine these days has multiple cores. Your computer has multiple cores, your phone has multiple cores. And that really means that those separate cores can run at a frequency that doesn't melt them, but by having more of them, they could do more things at the same time. And that works very, very nicely for computers for daily use, actually, because the things that they have to run are simultaneous. You might have your mail clients as well as your word processor, as well as running some computation, and they're doing different things, and different cores could do that. So that's fine. What if you need all those cores for a single task? And that is something that we'll talk about a little bit more. That's when you need parallel programming. So just running more things, separate things on different cores is not so difficult. You just give each core a different thing to do, fine. What if they all have to work together on a similar or on one task? That is parallel programming. So when we're trying to, when we are faced with a problem that is too big or too slow, and we want to run it on a supercomputer, it means running in parallel. Now, I already said this a bit, but there's this thing called Moore's law. You might have heard of it. Moore's law says that the number of transistors that can be placed inexpensively on an intricate circuit doubles approximately every 2 years. And so here's a plot to fairly recent, and it's remarkably true. This Moore's law was expressed, I think, somewhere in the 70s. So this is amazing that held. But it's not something that says that the computers have to be faster. It just means there's more transistors, which can also mean just more cores, as I just explained. So that's what this says. So Moore's law so far holds. Even that will eventually come to an end, and the signs are there. What we have at the end of the day in supercomputers is more cores at a fixed clock speed. Let's see if there's any questions here. I see some questions about how to log into the cluster, but I'll talk about that later. If you can try it out, the instructions are on the website, but I'll go through that in a little while. Okay, so yeah, more cores, great, that's faster, right? And so in principle, yes, because they are workers and they can do work. But you can't simply throw more cores at a computation. The computation has been programmed usually and almost always in a way that expresses an algorithm, and the algorithm says, do this, then do that, then do that, then do that. It's a serial list of things to do. And in many cases, the order of these steps matters. So really, unless you change or add specifications to that list of instructions as to what can be done by different cores, the only thing you can do is run that set of instructions on a single core. The other cores aren't doing anything. So you can ask for more cores. You can have a 40-core machine and run a code that you ran on your laptop that was too slow, and it will still run too slow because it will only use that one core. It hasn't been told how to run on different codes, and that can't be automated because there's implicit assumptions on what comes first and next then, which the computer can't assume or can't figure out whether they can be relaxed from. Okay, so more cores is a bit like having more workers, right? And so that gives a nice analogy with sort of the human resources dilemma. If you have a job that needs to get done faster, but you can't hire faster people, what can you do? Well, you can hire more people, but now if they all have to work on the same project, then you have to alter the workflow so that it will work. A single person might be able to do something, but all his or her actions might interconnect. One has to be done first. So now you have to split up this work in a way that makes sense. So divide and conquer. So even splitting up the work, telling which worker, telling the workers what to do, is a bit of overhead. You have to rethink and make sure that this can be done at the same time. Then you probably have to, at the end, glue things back together. So this requires some sort of administrative overhead. You have to make sure all the workers are busy all the time, or else, again, you have no benefit of having these extra cores. And if you don't have a lot of work to do, what you'll find is that this additional administration of or coordination of workers is actually more, takes more time than the actual work. I mean, imagine having to tie the shoelaces of one shoe and having 100 people trying to help you. It's not going to go very fast. So we'll need to think about how to do this, and we'll come up with some strategies. But first, we need to understand the lowest level of these things. Like, what kind of hardware architecture are we talking about? Because that's going to dictate what the workers are, essentially. And that will be our first step in understanding how to deal with supercomputers. So let's talk about architectures. There are some questions here. Let me see. So if we can have more transistors for more cores, why not use more transistors for more speed? So the reason is that if you make those transistors go faster, they will consume more energy. It's basically the energy consumption goes as like the third law of the frequency. So I make them twice as fast and need eight times as much energy. So it's both. First, that energy has to be dissipated, so it produces heat. So there's the cooling issue, which is now 8 times as much of an issue as it was before. It was 2 times faster. But also, it is not very economical to make something that takes 8 times as much energy for a 2-fold speed up. And especially since these machines are getting really large and not particularly environmentally friendly if we did that. So it's not just a matter of melting, which you could solve potentially. It's also a matter of diminishing returns. You don't want to pay 4 times as much for basically the same results, and also that means burning 4 times as much energy, and a lot of the energy is still not particularly green. So instead, if you could divide the work into 2 cores that are running at that lower clock speed, now you basically are 4 times more efficient in terms of costs, but also in terms of pollution. So that's sort of a win-win. The loss is that we now have to deal with the fact that we have to divide the work. Some people are looking ahead at the problem, so I'll get to that later if you don't mind. Okay, so what kind of architectures do we have then that are multiple cores? So there's different conceptual architectures. Modern computers, supercomputers, tend to combine them all together, but let's do them one at a time. Sorry. So we'll consider your own standalone computer or laptop is one of these circles combined with a square. So core number 0, that is one computer core. Say that's one computer. It has its own memory, and so the little square is meant to be its memory. And then there's another computer called core 2 that has a CPU, it has a core. By the way, CPU, core, chips, I kind of use them interchangeably at this stage. They're computer chips that can do computation. So core number 2 has some memory because it's in its own box. It's a different computer. It has its own box. It's isolated from core 1 and core 3 and core 4. Basically, I have 4 computers here. And now all I do is I connect them with a network. So a wire, there's a network card, and then they plug in some Ethernet cables. And now they can, in principle, communicate with one another. So they could send a bit of information. So core 1 could send a bit of information to core 2 that I can receive it and do with it whatever it wants to do. This is actually not too different from actually having several workers, like working on a project with several people. You have to talk to one another to coordinate, and this is the talking to. And sometimes you might have to give somebody some information, so that's data flow. It's the same with these clusters. So clusters are separate computers that are connected with the network. And one of the nice things about it is it's fairly easy to build because the computers themselves, the separate computers, are fairly standard. Like they get specialized to fit into a data center, but other than that, they're pretty much the same kind of architecture as you would find in a regular computer. And then you invest in a fancy network so that at least this data transfer is as fast as it can be. And there you go, you have your cluster. So these are called distributed memory systems because each core has its own memory. So remember, one of the cases you might want to use a supercomputer is because you need more memory. Say this is, let's say, 16 gigs for one of those squares, and I need 64. I now have 64, but they're all divided up. They're separate. So I would have to be very careful to make sure that the right piece of the puzzle is in the right spot. So this is a distributed memory system. And but as I said, it's just connecting computers that otherwise would be too small. So it's a very popular and cost-effective way to do things. But to program this, we have to think about transferring the data between these different memories, and that's done with a technique called message passing. So there's a standard message passing interface library that people use in their programs to explicitly send data from one core to another and receive data from another core, and that's kind of how you have to do this. So that's the loss that I was talking about. You have to program these things very explicitly to be able to coordinate the work between the different cores. So that's a cluster. For a while, these were very popular because you could make them fairly easy. And for a while, they did have just a single core. Multi-core computers came around the time when the clock speeds no longer increased, right? So that made sense. But before that, this was a very common way to make a supercomputer. Another way to make a better, faster computer is to basically glue all of this memory together and have one big blob of memory and different cores accessing that memory. That is how your typical computer that is a multi-core computer works nowadays. So your laptop, if it has like 4 cores, this is kind of what it has. There's one big blob of memory, and all these cores can read and write to that memory. And so that sounds like a much nicer way because you don't have to communicate, it would seem, but you are. You just the cores are now communicating through memory. And there's some tricky things there too, because you might want to make sure that different cores aren't stepping on each other's toes, basically writing to the same memory location at the same time. So there's other disadvantages here too, but it is a nice model because you don't have to think about the divisions of your data too much. The trouble with this is that building this out to many cores is expensive. There's ways in which the different cores have to be told when something changes in memory. The cores themselves, when they're computing and if something's ready, it still has to be put in memory. and maybe core 3 needs what core 1 wants. So there's a whole memory subsystem that has to be built to support multiple cores acting on a single memory. And that at some point breaks. It no longer is feasible to do that in a sort of efficient way or in a cost-effective way. So you find that the number of cores that you can run in a multi-core computer is limited. It's getting very large. Our main supercomputer at Synapse, Niagara, has 40 cores per say node in the network, and so those 40 cores C1 memory, that's pretty large. Our previous one had 16, so it goes up, but it doesn't go up as much as you would want the systems to grow. So what you'll find often is that you get multi-core computers that become the nodes, and then they're combined with this cluster idea, but now every core here is becomes a multi-core machine. So you now have to do both shared memory programming for what happens in each node and message passing interfacing to go across nodes. So the main model of programming this is threads. And is threads. And so that's really just a way to say each core does its own sequence of actions. One of the ways to program threads is OpenMP, but it doesn't really matter as long as you know that this exists. Okay. Seeing a few questions. Okay, so let's talk a little bit about core and CPU and processor, because they all used to mean the same when we were in this single core arena. In the single core, people used to call them CPUs, central processing units. There was one of them, and there was also the processor. So and then there was some memory. So that then grew out, and people start to mean different things with different words. So manufacturers like to call a CPU the whole thing. So if it has multiple cores, that's still one CPU. Programmers often don't. They often say a CPU is one worker. And so they might not agree on what a CPU really is. It's a central processing unit, but whether that unit has subunits is up for debate. That's why I try to work with the word core as much as possible, because it's less ambiguous. A multi-core CPU, say a 4-core CPU, will have 4 cores. Each of these cores can be thought of as a single processing unit that can take a set of instructions and run them without interruption. So you could run a program on one of those, and it would run as fast as it would have on an old-time non-multi-core machine. And then you just have 4 of those, and that's it. The connecting factor would there be the memory, but as far as instructions are concerned, that's a core. So a core is a single processing, a single worker. And so that's also in line. And for that, programmers and hardware makers, they tend to kind of agree. When they talk about cores, this is kind of what they mean, until you talk to operating system people that can talk about virtual cores. I'm not going to go into that in this lecture. I think that goes too far. But there are cases where you have virtual cores that are then yet another thing. But cores are physical processing units that can take one thread of execution, so one program, and run it at given clock speed. And then if you have multiple cores, you could run multiple programs on each of these different cores, and they wouldn't interfere. And then there's a remark by Bruno. It's of course in matter of fact even more complex, but a core is a core. That's my basic unit, and CPUs people mean different things by that. Okay, so that's multi-core clusters. There's one more important architecture that plays a role in supercomputers. Those are the so-called accelerators. And you have to think of graphics cards. Here's a graphics card. Graphics cards have to be able to produce pictures with many, many pixels at a very fast rate. And to compute the color of each pixel, that's a computation. And so what these are really good at are producing massively parallel computations of basically the same kind of thing with a slightly different input and a slightly different output, but with millions of pixels at the same time. Turns out that that technique, that architecture, or that technology can also be used to compute non-graphics things, as long as it's the same level of parallelism, where you have, say, a lot of data, and they all have to be processed in the same way, and then the output is, again, it's a lot of data, but it's all the same thread, basically the same algorithm for each pixel. They're no longer pixels, now they're data points. Then this might fit very well on a GPU architecture. So there's ways to take, if you have a graphics card of the right type, there's ways to program them in what's called general purpose GPU programming. So that's not, so you're programming a graphics card. GPU stands for graphics processing unit. So you have a graphics card, it's good for graphics, but there's also a way to make it good for general purpose. These days, people don't say GPU anymore, they just say GPU programming, because it's now so common that it's just a thing. But that is what this is. And these are accelerators. These are typically separate cards that are plugged into the computer, and they have to be programmed separately. The architecture is different. So the programming is a little bit of an additional issue. There's different programming languages and models. CUDA works for NVIDIA cards. If you have AMD cards, there's HIP. OpenACC is something that works within traditional programming languages like C and C++ and Fortran, but then has what is called offloading to the accelerators, same with OpenMP. So it's yet another level of different architecture that you have to program for. And there is no good way to take a program that ran on your single core machine and either make it automatically work for a shared memory machine, a cluster, or an accelerator. In all cases, you're going to have to port the code, rewrite some of it, express what can be done in parallel, and make sure the instructions land on the right piece of hardware. And in this case, the hardware is so different that when you talk about these kind of systems, you talk about heterogeneous computing. I didn't spell that right here. So you have some code that runs on the CPU, so the cores, the main cores of the computer, and some on the GPU, on the graphics card. And you might want to balance that, or sometimes you run everything on the graphics card and everything on the and nothing on the computer itself. So that's another. And as I said, these are machines that are these are architectures that are very simple. They can't do a lot of complex things, but they can do simple things very fast in parallel. So for some applications, this is great. You have to think of things like machine learning or molecular dynamics simulations or things like that, where you have, say, a lot of particles or a lot of data points, the same thing has to happen. They are really good at that. Other applications might not run as efficiently on accelerators because they have to constantly do different things for different data points. But because of simplicity, they can be made much larger with many more cores than you could in a general purpose chip. Okay, so let's look at some examples of supercomputers. There's a list that is composed of the top 500 fastest supercomputers in the world. People submit their computers to it. They have to run a benchmark called HPL or LINPACK. And then whoever is fastest gets on the top. And so they rank them. They make the list every half year. The latest list just came out. And here are some of the top contenders, and I also picked out the ones that we have. So the top one is Fugaku. That is a computer that is in Japan at the Riken Institute. And it has a lot of nodes. This one is one of those typical cluster computers. So 150,000 nodes. And each of those, so when I say nodes, I really mean like one of those computers, right? So multi-core computers that are then connected into the network. So really think of, let's just go back. Really think of this picture. This is a node, except now it will have multiple cores. Okay? So this one has almost 160,000 of those nodes, and each of the nodes still has 48 cores. They can then talk to the same memory. So there's 32 gigabyte of memory in each of those nodes that is shared among the 48 cores. They can all use whatever part they want. There are no graphics cards in that, no GPUs. And then there's a fancy network. It's called the Tofu network. It's a kind of torus that connects these many nodes together, and that is the current fastest supercomputer in the world that they want you to know about. The second so that's in Japan. The second fastest is in the States at the Oak Ridge National Labs, called Summit, and it takes quite a different approach. It only has 4,608 nodes. Each of them have 44 CPU cores. It's hard to imagine how that could be the number 2 in the list if that was all they had. But then each of them has 6 GPUs and a bunch of memory, 600 gigabytes per node. And those GPUs are very powerful, such that this 4,000 or almost 5,000 node system is almost as fast, or can almost beat the number 1. Not really almost, but it's in the same order of magnitude. So that shows you how much more powerful these GPUs are for this particular application. So what they've done in Nikon is really look at what are the applications people have to run, and how well do they run if we build our next system with GPUs, and how well do they run if we build them just without. And turns out for the applications that they need to run, in a lot of cases, it didn't make sense to buy GPUs. They're more expensive and you get less of them than to make, so say, non-accelerated nodes, just plain cores. They're not that plain. They're of a special fabrication. Fujitsu makes them, but still, no GPUs in there is what came out of their needs assessment. So it's one thing to say, well, GPUs are much more efficient, aren't they? But they aren't if you're not getting your work done, right? You're still burning the energy, and you're not getting as much work done as you would with this machine. So it's all a matter of science per greenhouse emission, I guess, although that's a hard quantity to measure. So Summit has done probably a similar thing, but they must have different applications that work well on GPUs, and that's the analysis they got. So jumping a few steps to number 113 is where Cynet's supercomputer is. It used to be at number 53 2 years ago when it was just installed. That's how it works, right? Newer systems are faster and jump you off your spot. But it's still the fastest computer in Canada in terms of this HPL score, and it too was actually designed in the same kind of fashion as Fugaku, looking at what people need to run and what kind of architecture can run that the most. And that, again, turned out in this case to be a non-GPU machine. So in this case, we have about 2,000 nodes. Each of them have 40 CPUs and almost 200 gigabytes of RAM. And they're again connected with a fast InfiniBand network. So the network is very important when you want to do these things at scale. So up to the 40 cores, it really doesn't matter what the network is, because you're not going off of your 40 cores in a node. But as soon as you need to scale out, a specialized network does become a bottleneck if you don't have one. We have a small GPU expansion, MIST, which is kind of like a mini Summit. But if you're doing GPU processing and you have something that works well on GPUs, so think of AI or molecular dynamics, maybe Niagara isn't your computer. And so if you're doing academic research, you don't have just access to Niagara. There's other systems like Cedar, Graham, and Beluga, and they have GPUs. And they are what we call general purpose machines. They don't aim to be able to scale out. That's why they don't perform at scale as fast as Niagara, even though they have more cores, particularly Cedar. So in that case, the GPUs are there for you to use, but they went for smaller jobs. We went for the Niagara is meant for the large parallel jobs, and does those very well. We also have a teach cluster. That's the one that you will be using. It's actually composed of some old nodes we had from a previous supercomputer, but it's 42 nodes. They're connected fairly well with the InfiniBand, but they have 16 cores each. You can see the previous generation in there, and 32 gigabytes of RAM. So it's fairly decent, but it is old. It's probably slower than your computer if you just run serially, but it is a parallel machine that we can use for teaching. Make sense? Keep an eye on the time here. So let's talk about parallel processing a little bit, because as I said, that's what we will have to do. So the point here is not that things are going faster. We have more cores. We have to give them all something to do. So you think of a multi-lane highway, except in this case, we want all these fast, well, they look fast cars here, to work together on something. So if they have to be streamlined like this, that's the way they run the fastest. Obviously, if they have to wait for one another, then that will make things slower. It also means that it shouldn't matter who's first. So it shouldn't be a race. It should be a nice collective streaming of traffic. And so what could destroy this concurrency, this idea that cores can run things at the same time, is data dependencies. If one stream, one thread produces a bit of result that another thread needs, that other thread will have to wait for it. So those are data dependencies. And a lot of parallel programming consists of figuring out what can be done at the same time, and then expressing that to either a compiler or not in another language, but in a way that the computer can do it. So first figure out what can be done at the same time, and then figure out how to tell it to the computer. Before that, you just have a serial program that the computer knows how to do from top to bottom, but not what can be done at the same time. So that's a serial code. So let's look at a best case scenario in which this is possible. Imagine that we're doing what's called a parameter sweep. We have a model that we want to compute through. There's a parameter in the model. In this case, it's called mu. And mu can take on different values, and we want to resolve for each of these different values. So the parameter mu is sweeping from 1 to 4, and for each case, we want an answer. These are completely separate computations. Each model can be computed separately, and so can be given to a different core and run at the same time. So this is a great way to get more computations done. Now, one way to measure that, to see how we're doing, is to measure what's called a throughput. And it means how many tasks can you do per unit time. And that's an important measure, more important than the speed of a single task, because in this case, we have many tasks to do. So it really matters what is the throughput, how many tasks can I do per time unit to know how fast my things go. So maximizing the throughput means doing as much as possible, getting as much done as possible. And in the case of these independent tasks, we can manipulate this a little bit, but it's also fairly intuitive. If you have 4 processors that run at the same time, your throughput goes from 1 over the basic time that one task takes to p times as much, where p is the number of processors. So throw p times as many processors at a problem, you get your answer. You get p times as much stuff done. That's also kind of intuitively, before you think about data dependencies, on what you would think you get. If you have a 4-core machine, that should be twice as fast as a 2-core machine. But you do need this independence for that to work out. So another way so people often plot these things to see how things scale as you increase the number of processors. So you will hear, when you talk to analysts at computing centers, they'll always talk about your scaling. Like you want more resources. Well, how does your application scale? What I mean is, if you increase the number of processors, how much faster does it become, or how much more stuff can you get done? And so in this case, we have what's called linear scaling. The throughput is linear with the number of processes. This is linear scaling. It's also perfect scaling. You can't really do much better. Another way to say pretty much the same thing is to look at speed up. How much faster did your whole problem become by having more processors? And so in this case, one way to express that is to take the serial time and divide it by the time that it takes if you take p processors. And again, in this ideal case, this is linear. So you need 4 processors, it is 4 times faster. Okay? These are called embarrassingly parallel applications, because the only thing you have to figure out is how to run them on different cores, but you don't have to separate anything. It's already separate. But that's not the common case. Usually you have non-ideal cases. So let's look at a non-ideal case. Here's a non-parallelizable algorithm. Suppose we have some experimental data, field data, and we want to integrate it, but sum it all up. maybe you want to take the average, but something like that. And it's a lot of data. So you would think that we can split this up. So integration here just means summing all of these data points. So we could sum, say it's 1 billion points. We could, and we have 4 cores, we could send 250 million to each core and say, well, why don't you sum those up? And that would be 4 times faster, right? But that's only the summing itself. There are non-parallelizable parts of this scheme where, first of all, we have to partition the data. The data comes from somewhere, we have to probably give it to the different cores one way or another, or even if all the cores can fetch the data themselves, we have to tell the cores where to get the data and what part of the data is theirs. So there's some overhead here. This is the administration part that I was talking about, to tell every core what to do, and then the different regions can be done separately. And then at the end, once each core has computed the sum of its region, it has to, the whole thing has to be summed up again. That's called a reduction, where you have several numbers that still have to be reduced down to a single number. But again, this one, since they all have to be summed together, they all depend on having these results, is not purely parallel, right? So this is a non-parallel region, and then we get the answer. So you've got partitioning overhead, so parallel overhead, and then there's some serial fraction of the computation, where all we can do really is to give it to a single core to finish it up. You might think, well, no, but that's a very small part, right? That's just a few additions. That's okay, right? I'm still pretty much doing parallel programming. So let's see that that's actually not as clear cut as you might think. So let's come up with a few definitions so we can quantify how well things speed up when we have this situation, which still is very close to the ideal case. So we're going to define T sub S as the time for the serial part. So that's the partition and the reduction, the stuff that's not parallelized. And then T sub P is going to be the time that I would need to do all regions, but in series, so one at a time. Okay, so if I had a single core, the time that this computation would take would be TS plus TP. So let's see. So we can compute the speed up. And the speed up is the serial time divided by the parallel time. The serial time here is TP plus TS. The parallel time gets slashed by a factor of P when we give it to P processes. But the serial time, we're going to assume here, doesn't change. Of course, there's some dependencies, but let's assume for the moment that it's fixed. Then this is our speed up, and it's not entirely insightful, but what's a nice way to formulate this is to look at what's called the serial fraction. So that's the time that it takes for the serial process divided by the whole time, in case you run serially. So that's F. There's a question whether the reduction is performed by a single core. Yes, that's what we're going to assume at this point. You certainly can't do it by every core, or every core would do the same thing, and then it still takes the same time TS, so you don't speed it up. So expressed in terms of F, you get this fairly compact formula, which is actually called Amdahl's law. So the speed up is 1 over F plus 1 minus F over P. So the serial fraction stands here. This is the parallel fraction, and it gets slashed by a factor of P. And it really is insightful just to plot this as a function of P for, say, a fairly small fraction. Say 5% of the time is spent in computing this reduction, and the rest is all parallelizable. Very quickly, even with just 5% serial fraction, you see you deviate from the ideal scaling, that's the blue line here, and you get, even at like 16 cores, you only get an 8 times speed up. And it just gets worse. In fact, it gets so worse that if you take infinitely many processors and you use it for this program, you're hit a limit. You hit an asymptote. Asymptotically, the speed up can't be any bigger than 1 over F. This makes sense because no matter what you do, you always have to do the serial part, right? So if the serial part was 5%, I always have to do that 5%. So if the rest of the time is vanishing, I still have that 5%, which is exactly, so 1 over 5% would be 20. So this would eventually plateau at 20. So that is annoying. This serial fraction is eventually going to win, even if there's a substantial part that can be parallelized. And this matters a lot if you have these large supercomputers. Now, there's a way to beat that. One way is to make sure your serial fraction is as small as possible. So whatever you can do to speed up the serial fraction is actually like well spent time if you know you're going to scale up to a large number of cores. If you don't, you want to speed up the part that takes the longest. But if you have a lot of cores, that serial fraction is going to be your bottleneck. Another way to beat it is to scale up. And the idea is that the larger the number of points you had to sum, which we've called n here, the system size, the smaller, relatively speaking, the serial fraction becomes. Right? In terms of summing these numbers, the more I have to do in the bulk of the computation, so this middle part, the parallelism part, the smaller as a fraction the remainder is. Right? So if you do that, you get into a regime that's called weak scaling. So rather than just making the number of processors larger, you at the same time make your system size equally larger. So 2 times as many points, 2 times as many processors. What happens then? And it turns out that in that case, if you again assume that the serial fraction is independent of p, etc., you see that as the system size increases, you get closer and closer to an ideal speed up. There's still crossover eventually, but for a fixed number of processors, you get more and more ideal scaling. So that means that if you scale up, your scaling becomes better. But it's a bit of cheat because for many cases your system size is a given. But if it isn't, or if you're just developing an algorithm, this can be a good way to say, hey, this is a good algorithm if you want to scale up by looking at the weak scaling analysis. Okay. Let's look at one more non-ideal case. And that's a case where we are dealing with what's called non-locality. And so in the previous case, we weren't worried about where the data was or where it had to go. But that's not typically true, especially if we have one of those clusters, and we do. Some of the data might be on a different node and now has to communicate through the network. And I already said the network is pretty fast, but it's still one of the slowest elements of your system. So computing on the node itself, the things that are in memory, is way faster than first sending the data over the network to a next node that then does the computation. So you want to compute basically where the data reside as much as possible. It's not always possible, but you want to minimize the data transfer in your computation when you think of it in a distributed way, because that takes more time. Now, there's many systems that sort of hide this locality. They use caches, etc. But at the end of the day, those are finite. So you might have a cache that keeps some of the data copied near the processors or something like that. So how do you influence this locality, though, is by changing how the data is accessed. And now it matters what kind of system you have a little bit. So if you have a shared memory system, you would think that you don't have to worry about non-locality because everything lives in that memory blob. But it turns out there's a hierarchy of memory blobs, and some of the memory lives close to a processor, but then it takes time for it to go to another processor. And so there's a whole memory subsystem that does all the communication for you. But it still means that if data is processed by one core and then subsequently by another core, that is slower than having it processed done by the same core. So you try to make sure that your data lives close to the core that used it last, which is a weird way to think about it, but it doesn't pay off if you're doing shared memory programming. In distributed memory, it's kind of opposite. It's not implicit at all. It's totally explicit. You want to make sure that the data is with the process that needs it, or you'll have to send it. So you'll very quickly realize that you're doing a lot of communication calls. You've probably not done the right thing. Okay, so there it's very obvious when you're doing a lot of communications because you're moving data explicitly. In file systems and in memory, what helps a lot too is that those are set up in a way where if you have, say, a big file and you read 1 byte of the file, actually the file system will give you not 1 byte, it will give you a whole bunch of bytes going, I'm already reading it, I'm just going to store these things, I already know where they are, so that if you have a need for the next byte, I already have it. And so that's a sort of linear model of files and of memory as well, where using data in a contiguous way, so streaming it, making sure that the data is close together in memory or in a file, helps a lot. And where that breaks down, and when you can see where you've done something wrong, is that when you don't do that. So in the same vein, if you have data and it's distributed among, say, 1 million files, they will be anywhere on the disk, and they will not be contiguous. And you open one file, the file system doesn't give you also some of the data of another file. That would actually be strange and probably not very secure. If you put them all in one file, if you grab the chunk of data you needed, so what was a previous file, it will then, the file system can also pull in already, say, the next file's content, which is now in the same file. And so you get that streaming. So so there's many levels at which this can help you if you know that, yes, it's pretending to be all the same, many files or one big file, but it isn't, because the way they are fetched. And then finally, another non-ideal case where you can't just do things in parallel and expect performance is when you have computations to do that do not take the same time. So in the case of our summation, we basically divided our data set in 4 batches that were equal size, and then they would take the same time. What if you don't know that ahead of time, right? What if they take different times to compute, say, the first batch than the other batch? Then some of these batches are going to be done before the slowest batch, and the slowest batch now sets the pace. That also means, if you don't know that ahead of time, that slowest batch, while it's finishing up, the other cores aren't doing anything. Okay. So imagine that we have, say, 32 computations to do, as an example. And they're all independent, and they all take some time, but we can't predict what. Maybe the whole point of it is to do some sort of a search. And then we don't know how long it will take to find things, but it will take different times for different things that we're searching for. Okay, so that will take different times. And we can't know how long it takes ahead of time, because that would mean that we basically already found it. So let's say we want to run these 32 computations on 8 cores. We could do it in this way, where we say, OK, I'll take my first 8 computations to do, and I'll just give them to different cores. So this is core 1, 2, 3, 4, 5, up to 8. They're all doing some work, but one of these cases takes a little longer. So imagine time running in the downward direction here. So the height of these bars is how long it takes. So this one takes longer, this second one, and all the other cores are just waiting. But I didn't know that because I have another set of 8 ready to go once this first set of 8 is done. So here's the second set of 8. It was a little bit more balanced by chance. And then when they are done, and you notice there's still some load imbalance here, some black unused spots. And then we have our third batch, and again, we have one of these bars being much longer, and therefore wasting the time in the other ones in a sense, but we didn't know. And then finally, we have our last batch. So there's a lot of unused computation time, which you can kind of see here, right? These voids are unused computation. It doesn't have to be that way, but this is a case where you have load imbalance. Now, one thing you could try to improve this, and then just to see what the speed up is by using 8 instead of not, is we only get a speed up of about 3.5, which corresponds to only 42% of the computation time used. We can do it differently and say, well, look, one of these cores here, number 6, was done after a while. Why do we wait for all of them to finish before it's given a new task? So let's give them a task as soon as they're done, right? Which we have to program in somehow, right? It's not the natural thing to do. If you do that, and you figure out how this all stacks together, you get a much better utilization. There's still some long parts that we just can't help. We don't have more things to do. By the time that this last one has gotten its task, there are no more tasks to give, right? So that's it. But still, we get a much better utilization. We get a speed up that is much better. And if we had more tasks, the scenario on the left side would stay inefficient, whereas the scenario on the right side would, much like the scale-up case before, would become more and more ideal. By the way, you could code this yourself, of course, giving new tasks, starting new tasks as soon as the task is done. You don't have to. There's a tool called Nonparallel that I have the reference to here that basically does that for you. And you just give it a bunch of tasks, and it will make sure that only 8 are running at the same time. 1 core is done, a new task is started, and so that's great. Questions? So I hope it became clear that since we're working on these parallel machines, there are things to keep in mind that mean that you don't automatically get a 40 times speed up because you have 40 cores. There's some work involved. Depending on what kind of machine you have to do it different way. Sometimes it's using GNU parallel. So if you have a bunch of serial processes, I don't know, you're doing sequence alignment or some sort of search algorithm, and they take different times. A tool like that is fairly easy to incorporate in what you're already doing, because you're probably doing a for loop over many cases. If you have one of those more complicated cases, like a fluid dynamics simulation or molecular dynamics simulation, or, you might want to use, you might have to change your program and actually go to the program. You probably have a compiled language there anyway. So if you have a lot of files, again, there are things you can do by making large files or combining them together. There's a question on whether tasks and cores are the same thing, and they're not. Cores are like the workers. Tasks are things to do. So in the case of summing our numbers, we have a set of numbers, say it's 1 billion numbers, and I have 4 workers that can sum things, and they all get data. So a task is adding a number to basically keeping a tally, but adding a number. That's the task. So I have like 1 billion of those tasks, and I have 4 workers that can do it. So a core is like a worker. It can do a task. And the tasks can take different times, as in the last case. So I have more tasks. So here these are the tasks, the squares of the task, but they're giving to a worker. So each column is a worker. Make a little bit more sense? Okay, so we're going to have to think about how we do things in parallel. Sometimes it's easy, sometimes it's more work. But we also have to think about the resources we're getting. And what we're getting is access to shared remote resources. Because the answer to a question, may I have a supercomputer, please, is almost always no. If you need a supercomputer, your computation or computations have outgrown your computer, right? But you don't run to the store and get a supercomputer, because very few people can afford one. So you'll have to get access to a supercomputer, but you're not the only one. You'll share that with potentially hundreds of thousands of other users that are also on that supercomputer, and that changes how you work on these computers, sort of on a day-to-day basis. We can access these computers remotely. That's great. We don't have to go there anymore and submit our punch cards and then go back and come back and get a result. Those days are over. We can just remotely log in. That's great, which allows for even more sharing and therefore more and bigger systems, which is potentially great, because if you share your system, it's not too long ago that research labs would get their own cluster. It wouldn't be very big, but as they were developing their software, the cluster was just sitting there doing nothing until the software was ready to run the analysis. Then it ran for a little while, and then the cluster was useful. And then the cluster was just basically doing nothing until the software development for the next batch was ready. And so what will happen if you share resources is that you'll have groups doing the same thing still, developing some software or some pipeline, or even waiting for data and then running it. But since they have different schedules, the system can be pretty much always used. There's always somebody ready to actually compute things. So shared resources get better utilization, better bang for your buck, and so that's good. And just as an example, for Niagara, where I, of course, have access to the utilization, it typically lies around 98%. Sometimes it dips a little bit because a big job has to start, but it's a well-utilized machine exactly because there's always some job that is ready to be run. Okay, but because they're shared and remote, you have to use the machines a bit differently from your own computer, which is a little unfortunate because you're probably very familiar with your own computer, but it is a small price to pay for the scale at which you can compute once you adopt these different ways. So it's a question whether you could use InfiniBand over the internet. And InfiniBand itself, no, because it's a specialized network that for some parts will need fiber and other parts. So it's a complicated system. You could run computations over the internet. The trouble is distance now becomes a real limiting factor. The speed of light is not infinite. And so people have done this, but more as a proof of principle. Hey, we can compute something that some of it runs in Japan, some of it runs in Europe, some of it runs in North America, but you don't get any good performance out of it. So it's the same idea where you want your data to be close, locally close to where you compute. It has to get there. So yes, you could do it, but what's called the latency, the time that it takes to wait for a bit of data, becomes so long that it's basically not worth doing. Now, if you have, though, if there are not much communication needed, though, then yes, you can do this. So there's a thing called grid computing, where, and for instance, the people at CERN in Europe, they use this a lot. They have a lot of events. They are a particle collider, right? A particle accelerator. They collide particles. They get events. They have to be analyzed. They send them all over the place, and that's because each event can be separately analyzed. And so it doesn't really, it's not a lot of data. The analysis takes some time. And so that is a global grid of computers that processes that. But it's because it's very what's called loosely coupled. Each of them doesn't have to do much. They eventually have to report back. But if you have, say, a simulation that takes that needs to communicate where different parts interact, then you definitely can't do that. So sometimes it works, but in many cases it's just not. It's not a good idea. Okay, so how are these supercomputers then differently? How do you work differently with them? What's so different? One of them is that they're remote, so now we have to connect to them somehow. So you're at your computer. We're going to call it the terminal because that's where everything ends. And you have to connect to a data center where the supercomputer is, and we will call that the server. Okay. And so now you have to connect remotely, and we are using, as I already mentioned, SSH, which stands for Secure Shell. It's an encrypted way of communicating. You can use passwords, you can use keys. There's ways to make it multi-factor. So there's a lot of security built into the algorithm that you can, with good practices, can use. But it's something that just takes text, basically old-style typing commands, and the supercomputer does or interprets it. Okay, so there's a command line, and yes, so there's no GUI, and there's two reasons for that. One, people have never needed one. In the old days, you couldn't get one. But the thing you're going to do with these supercomputers, we'll see, is the GUIs won't help you. The GUIs, you can only do particularly fixed things, right? Or a graphical user interface. You can click, you can find a menu. First of all, that will be kind of slow over this remote network, but even so, if you want to do something new, and research is almost always new, it's probably not exactly there. And for the most part, when you're using a graphical user interface, the computer is just waiting for you to do things. So it's also kind of inefficient. That's like that, and the fact that there's nobody in HPC uses a GUI. If you need large-scale stuff, you're not going to be clicking on. Imagine typing in by hand a million data points. You're not going to do that. You'll have a different way to do that. So as a first try of this, you've all gotten access to the Teach cluster if you've registered, but you have to look up what your account is. So you have an account on the education site that you used, and I hope you took the test already. By the way, the attendance code was 1 if you haven't taken the test yet. On that same web page, on the right, let's see if I still have it here. Yeah, make this a little bit bigger. Is the login info. And you will have gotten here a signed user ID. So that's what your needs to use. So it's not Arzon, which is my my login for the education site. It's some other start with LCL underscore, etc. And there's an email associated with it. That's why we asked you for your email when you registered. And now you have to use those two to get your password set. So this is a security issue, we used to just give you a password, but then that's not particularly secure. You can choose your own by going to this site here and setting your password by entering these two things. It also asks you if you're a human, and it will send you a confirmation code, and then you can set your password. So you'll have a password that is then associated with your signed user ID, your LCL. Even if you already have a signed account or a Compute Canada account for these workshops, we're just using these LCL accounts just to make it uniform for everybody. Also, if you do something accidentally wrong, you mess up this temporary account, but your old account is still fine. So it's beneficial. So try and get that done if you haven't yet, and then try to log into the Teach cluster. Let's see what kind of time we have. Yeah, so we're almost done with time. So we're going to try this, and then on Wednesday, I think I'll postpone the rest to Wednesday, and then we can look at that. But this is a good thing to get going to make sure you can get your password. So if I click on it, it'll go to something that looks like this. And here's my user ID and an email that I have to do. I won't do it now, and then once you have that, you can SSH. So again, if you're on Windows and you don't have an SSH client, download Mobile Xterm. There's a bunch of links here too. If you click on links, one of the links I think goes to Mobile Xterm. Install it. If not, you can get a terminal. So something like that. This is my local terminal. This is the console, it's called sometimes in some cases. And I can type SSH -y, which is actually optional, but let me do it anyway. LCL. Let's copy it. Oh, I think I did it right. It's only 1 underscore. If you've got the PDF from the website, copy and pasting, you have to be careful with that. Underscores tend to not survive copy and pasting. But then it will ask you for your passwords. And so the password you just chose, and then it will tell you something like this. And so we're now no longer on our own machine. I am now logged into the Teach cluster. My name here is just LCL_UOT. There's not much in here. If you know a little bit of Linux, there's no files here. We'll be using this account on the Teach cluster to do everything, all the exercises. Let me know if there's any issues with either getting the password set up or accessing the Teach cluster. Because this is actually a good time to make sure that if you have any issues, to just resolve them now, because otherwise you won't be able to do any of the hands-on stuff. So try this, and in the meantime, let me just. Okay, so that's what we have. Now, we're not going to transfer any files, but just for completeness, I have the way you could download things either from the internet or copy files from your computer to Teach. with either the wget command or the scopy command, but I won't go into that. That's for another time. So yes, these are temporary accounts just for this course. We'll leave them open for the rest of the summer. So they'll be shut off somewhere at the beginning of September. So you could play around with it a little bit more. Or if you're taking one of the other workshops in summer, you'll basically get just one temporary account. So we're on the login node here. What does that mean? It's a cluster. Teach is a cluster. It has 42 nodes. One of the nodes is set apart, and when you log in, you're on that node. The node has 16 cores. So if we're about 50 people here, there's 50 people sharing 16 cores. And you can imagine that that's not particularly efficient. But that's also not where we're going to be running our computations. We'll be running them on some of the other 41 cores, 41 nodes. But we can log into those directly. We'll find that what we have to do to get access to those other cores or those other nodes is to write a little thing called a job script. It's a script, it's a text file with a few lines that specify how many nodes you need or how many cores, for how long, and give some other things. And then that basically specifies your resource requests. And then the rest of this job script actually says what you want to do once you have those resources. So that's kind of how it works. So this is because it's shared. If people just log in willy-nilly to a random node and started running things, suddenly your application becomes slower because somebody else is running there too. That is just an unworkable situation. So people have to submit these job scripts that specify the resources that they want, and then submit them to what's called a scheduler. The scheduler has the job of the scheduler is to take this long list of people submitting jobs and see who runs first and when, in both as efficient as possible, so no unused cores, but also in a fair way, where if you've run a lot in the past, maybe it's time for somebody else to run. And so it takes all of these things into account in a complicated scheme called fair share, but that's its job. Then what else? Okay, so that's your job scripts. That's the compute nodes. There's a disk system. There's a storage system. There's actually several ones. There's a home and a scratch. Your home is where you sort of put your backed up stuff. Your scratch is where you work. Let's see if I can show that. So I am in home right now. And the home is encoded in $home. So if I echo $home, it actually tells me what the directory is. It's kind of a long directory. Slashes obviously dividing subdirectories. Scratch is another directory. Scratch is bigger than home. Scratch is not backed up, but that's because it is bigger. Home is backed up. And you should do all of your temporary files on Scratch. In fact, you can't write to home in most compute nodes. So once you've gotten in, the next job is to try to submit a job. And so here's, we'll go through this, and that's where we'll probably end. So you'll log into the Teach cluster. Then you change to your Scratch folder, and there's a good reason for that. You can only write to Scratch. This is going to be a job, and a job should run from Scratch. You copy the material that you need for the course. So it should be here. I'm going to try this out because this sometimes fails. So copy, CP stands for copy, -R stands for recursively, so a whole directory. Otherwise, we don't get, we get just a single file. This is the path, SciNet course SS 2021. And this is the third week, so 3_intro HPC. That's the source, and then you have to give a destination. So just give it $scratch again. Capitalization matters, by the way, so make sure you type that right. So, SciNet course 2021. C to Scratch. There we go. Now it's in Scratch, so I don't see it here. I have to CD to Scratch to get there. Scratch. Go. And now if I type ls, it will see that file. I must have done this before. I'll see the directory. So here's the directory. So we cd to that directory, a specific directory inside of Scratch. And then we can submit the job. So let's do that. Sorry, this is a very long prompt and a large font. So I can submit something to the JavaScript to the scheduler with sbatch. And so the JavaScript is called sweep bond break.sh, and the way you submit it is by saying sbatch. And that's all you should need. And it says submitted a job, and it gives you a number. Okay, so we've done that. And they can check whether or not it's actually in the queue with sq me. Smaller here. Let's try it again. Okay, so it says it's running. It says how much time is left, and some other things. There's one node, one CPU. It gives you the node it's running on. After a while, it will be done. This one takes quite a while, so it won't wait for it to be finished. But once it's done, it will have created a file. And the file is called slurm-something. So unfortunately, this is an old name, so never mind the sweep bond break output. You should be looking for slurm-something. And if you look carefully, the dash number here was exactly the number of the job. So each number has a job. Each job has a number. And the number is encoded in the output file. So we can look at that output file. And it basically has a record of what's being done. This is a bunch of simulations. And so I'm going to try and find a logical break here. But this is a bunch of simulations that it will do in serial, and we will eventually do them in parallel. Yeah. So let's continue this on Wednesday. I don't want to take up your time more than you might like. You can look ahead if you want to the assignment. It is posted. That's fine. And then if you have questions on Wednesday about that, I'm perfectly willing to address them. But if you manage to do even these things, it means that you've gotten an account on a supercomputer, an old one, but still, and you've actually run something on a supercomputer, even though you don't know yet what it was that you ran. But that in itself means you can say that you've used a supercomputer. The attendance number of today was 1. Any questions? No, I think the login instructions and how to get the material are only on the slides, but the slides are on the website, right? Either here where it says slides. Go there. You can download them too as a PDF. So. Yes, so we're recording these lectures. The question is if they will be available, and yes, the recording will be available. Just as where it says slides, there will be something saying recording. It can take a few hours for the post-processing and the copying to be done, but that will be there, yes. So there's a question: what is more efficient, using more cores or more nodes? And the thing is, with more nodes, you get more cores, right? So that's so it's always more cores. But the question is say for the case of the teach cluster that has 16 cores per node, the question is 16 cores enough? And is it worth going beyond that? Because if you do go across node, You can no longer use shared memory. So you better have an application that can run on it on separate nodes, an MPI application. And you also have to worry about the scaling. Like, am I still getting some speed up, or is these 16 cores, like, am I already sort of maxing out my speed up anyway? Okay. For those of you that haven't done the attendance test yet, the test is under tests. So go under tests. You'll see attendance tests here. You click on it, and then you can start taking the test. It's a bit silly because it's obviously made for tests with more than one question, but it's still, it says begin, and then you can say, what is the attendance code? And you enter your attendance code, you submit it, and then that's it. That means you will have been registered as participating today. Okay. Any more questions? Okay, if not, then I think we'll leave it at that, and I'll see you all virtually on Wednesday again, same time. And we'll finish the slides. There's a bit more to talk about. I'll explain exactly what the idea is about the assignment. But as I said, you can also read ahead or look at the website and try it, and come with some questions.